Okay, so today I'm going to speak about the equation state of QCD, which has a direct relevance to the neutron star physics. And recently, there have been a number of new concepts developed after the revolutionary discovery of neutron star and theoretical study of dense QCD. So those concepts should be tested. And that's the reason why we are working on isospin QCD, for which lattice QCD calculations are available. So this work is done in collaboration with Ryuji Chiba in Tohoku University. He is my student. So let me briefly sketch the picture we have been developing. So we have several distinct regimes, and of course, at low density, we have nuclear matter, where neutrons interact through meson exchange, or more microscopically, it is quark exchange. And in dilute regime, neutrons are well-defined object, and the nuclear matter calculations are just fine. Beyond twice nuclear saturation density, it is known that many body forces become very important. And that means also there are many quark exchange among baryons. And in such situation, it is natural to expect the structural change of hadrons, as well as the excitation, like hyperons, delta, etc., etc. And in fact, this regime is most difficult theoretically because degrees of freedom are not clear-cut. On the other hand, this regime is interesting in the context of neutron star physics. Beyond 5 times nuclear saturation density, our description becomes simpler after baryons overlap, because degrees of freedom are now clear-cut. It is quarks. And in that sense, this regime can be regarded as quark matter. But this quark matter should be distinguished from the conventional weakly coupled quark matter, because modern perturbative QCD predict its breakdown at density less than 40 times nuclear saturation density. Therefore, this matter, quark matter, should be regarded as strongly correlated quark matter, which has not been explored very well. So in what follows, in this talk, I will mainly focus on the physics between 2 and 5 times nuclear saturation density, and also the physics between 5 and 40 times nuclear saturation density. So this is the plan. So let me briefly mention what is the indication from low density nuclear physics and the neutron star observation. So low density nuclear constraint and the radius constraint of the 2.1 solar mass neutron star seem to suggest the QCD equation state should be a soft stiff type. So here, a soft equation state means pressure is low at the given energy density. And if we say stiff EOS, pressure is large at the given energy density. And in order to achieve this soft to stiff combination, so we have to start with the soft equation state at low density. But this equation state must develop into stiff equation state at high density. And in between, there must be rapid growth of the pressure as a function of energy density. But this slope, dpd epsilon, is nothing but the square of the sound velocity, which must be smaller than the square of light velocity. So this is a so-called causality constraint. So what we can see from this argument is the low density region and high density region constrain each other through the causality constraint. Therefore, the physics in different density domain are actually highly correlated. In other words, the physics of nuclear matter and the physics of quark matter should constrain each other, and they must be related. So in order to achieve this soft to stiff combination, so the simplest way to connect low density and high density is to just consider the smooth curve. And if we try to include more structure in between, we have more danger to violate causality constraint. So this consideration leads us to the picture of quark-hadron continuity or quark-hadron crossover as our baseline argument. And in this picture, typically, generic trend is sound velocity develop a peak somewhere between 2 and 5 times nuclear saturation density. And after that, sound velocity gradually relaxes to the so-called conformal value when kinetic energy dominates over the interaction energy. So this peak structure seems to be associated with the quark degrees of freedom. And in fact, if we look at purely nucleonic computation, the sound velocity gently becomes larger gradually and violate the causality constraint somewhere around 5 times nuclear saturation density. So this trend is actually due to because the nuclear matter calculation typically rely on the many body forces, like 3-body, 4-body forces, which can achieve the stiff equation state, but has some problem in convergence. So this is the understanding of this peak structure is a hot topic in the community of dense QCD, and we want to have some microscopic insights. And in that context, we have been working on some dual description between nucleonic and quark matter description using some schematic model. So let me briefly mention about this schematic model. So this dual description it consists of 3 important information. The first information is about a quark momentum distribution in a single baryon, okay, like quark distribution in a single nucleon. And the second important information is occupation probability of baryonic state in dense matter. For example, in the case of ideal baryon gas, in that case, baryons occupy states from 0 to Fermi momentum with probability 1. Like step function. And by picking up the quark contribution from each baryon, okay, then we can sum up them and to calculate the occupation probability of quark states, which look like something like this. Okay. So as we increase ideal baryon gas, density of ideal baryon gas, then the occupation probability develop into the horizontal direction like this. And on the other hand, we can calculate that the quark occupation probability simply grow into the vertical direction. Okay, so this is the behavior for ideal baryon gas. But this, as we increase density more and more, then quark occupation probability eventually hit the upper bound. Since this is a probability, it has upper bound 1. Therefore, after this happens, we have to change something. Because if we try to keep increasing baryon density, as in usual ideal baryon gas, then we would violate the quark principle. And in fact, after states of quark are saturated, so after this happens, we have to put the baryon into high momentum state in order to avoid the violation of quark principle. And in this way, relativistic baryon appear, even though the density is not so high. And actually, this is the essence of recent Maclaurin-Reddy model based on the quark matter. And because the relativistic baryon appear, equation state is naturally stiff, and it develops a peak. So the main message of this argument is quark substructure is really important. But so far, unfortunately, all of these arguments are kind of some schematic and qualitative discussion. And in the next step, we want to proceed to more some sophisticated discussion based on explicit treatment of interaction. And for that purpose, isospin QCD is useful as a laboratory because there is no sign problem. And in this study of isospin QCD, we are particularly interested in the following topic. The first, hadron to quark transition. And to describe the hadron to quark transition, we need a model which can describe both hadrons and also a quark. Okay, and we want to understand the behavior of quark substructure, the impact of quark substructure effects on the equation state. And the second important topic is how to describe strongly correlated quark matter before reaching the perturbative QCD domain. So particularly, we are interested in the possible KSI particle regime in the similar sense as the constant quark model. In the constant quark model, the interactions are not weak. Nevertheless, KSI particle picture is at work. So we expect a similar qualitative regime in the regime in quark matter before reaching the weakly coupled regime. So this topic, what we want to study. So let me briefly mention some overall feature of isospin QCD. So isospin QCD is QCD with isospin chemical potential. So here isospin chemical potential mu I is just the up quark chemical potential minus down quark chemical potential. And during my discussion, I will use saturation density and not as our unit, because we want to study the relationship between isospin QCD and our physical QCD in neutron star context. Okay, so as we increase the isospin chemical potential, then the first excitation to appear is just a pion, okay, instead of a nucleon. So this is a specific feature for isospin QCD. And as we increase isospin chemical potential, that increases the up quark chemical potential and reduce the down quark chemical potential. So therefore, as we increase isospin chemical potential, we develop a U quark Fermi C and anti-down quark Fermi C. And these two Fermi C actually can generate the so-called some sort of Cooper pairing between U quark and anti-D quark. And also, there is U quark hole and anti-down quark hole, which can make a pair pi minus. So these pairing generate a so-called pion condensate in the same mechanism as the BCS pairing. And so the size of quark mass gap is from this BCS pairing is, so if we naively assume the usual BCS formula between critical temperature and gap, so critical temperature is known to be the order of 160 MeV from lattice calculation. And if we apply naive BC estimate, the size of gap is order 300 MeV. Okay, so this is the what would happen at the non-perturbative discussion. And as we increase the isospin chemical potential, what happens first is, so we have first hadronic phase. And when mu I reaches m pi over 2, we start to have the pion condensate in BEC regime. And around m pi, so BEC regime quickly end at density around 0.3 times nuclear saturation density. And after that, quark substructure effect become important, as I will discuss later. And one important message here is the quark substructure effect is important, become important at low density. And actually, this density is substantially lower than the density where the pion overlap, especially. So if we look at the radius of pion, it is about 0.7 Fermi. And those pion overlap at density about 5 times nuclear saturation density. So this quark matter onset of quark degrees of freedom become important at the density substantially lower than the naive expectation of a pion overlap. Okay, so this is the content of my talk. Okay, so next I will discuss some basic property of quark meson model and compare 3-level result and 1-loop result. And at this level of discussion, we already see the importance of quark substructure. Then I will relate the physics of microphysics, and I will discuss the impact of microphysics on the equation of state. And then after discussing the crossover regime from BC to BCS, I will next move to the discussion for the strongly correlated quark matter regime and discuss a recent issue about conformality and trace anomaly, emphasizing the power correction to the pure perturbative QCD calculation. And then I will summarize my talk. Okay, so by the way, any question? Fine. Okay, so let me continue. So, for our study of isospin QCD, we will look at. We will use the isospin. The quark meson model. So quark meson model includes, of course, meson, which is relevant at low density, and the quark degrees of freedom, which is relevant at high density. And isospin chemical potential are coupled to a charged pion, pi plus and pi minus, and also quark. So within this model, the outline of calculations are as follows. So at the first step, so we define the model by renormalizing the model in vacuum. And for this renormalization procedure, we limit ourselves to the leading energy contribution, ignoring the meson loop correction. Then, after renormalizing model, we construct a one-loop effective potential as a function of effective mass and the pion condensate within mean field treatment. And then we will minimize the mean field thermodynamic potential, and then to find the solution for effective mass and the gap. So after finding this optimized value of a mean field, we substitute those value into the substitute back to the those mean field value to the one loop effective potential, and that corresponds to the thermodynamic potential, which is the function of mu I. So this is the procedure. So let me briefly mention how we renormalize the model. So in this talk, so I will discuss the so-called on-shell renormalization, which has been used by Ado Hikari et al. For this model. So basically, framework is just the same. So, so the advantage of using this on-shell renormalization is we can tune our parameter of model already at the tree-level calculation. Because on-shell renormalization require the self-energy correction to vanish at all order of loop computations. So and so renormalization procedure can be done as in usual way. So we renormalize 2-point function and also a 4-point function, and that's it. And at one loop level, the 2-point function for the meson propagator can be renormalized by computing a quark loop correction to the meson propagator. So there is a one loop correction to the self-energy, and we also have a counter term. And as I said, on-shell renormalization require the self-energy correction to vanish at any loop order in vacuum. And so this is a condition. And we have the renormalization of mass parameter and the renormalization of residue parameter. And in on-shell renormalization, we treat sigma meson and pi meson, pion, in different way. But the UV divergent part are just common because of the O4 symmetry. And this finite part of the counter term can be constrained by the symmetry also. Okay, so this is a renormalization of 2-point function. And there are also renormalization of 4-point function. But it is more convenient to just look at the renormalization of a single quark energy instead of directly treating 4-point function. So one loop correction comes from the quark contribution, quark one loop contribution, which is UV divergent because it integrates over the whole Dirac contribution. And if we use the dimensional regularization, so it is given by UV divergent term coupled to the quartic order of effective mass or condensate. And this term can be cancelled, divergence can be cancelled by the vertex counter term. And at this stage, we completely fix the UV divergent counter term for 2-point function and 4-point function. Okay. But in order to assure the cancellation of divergence in different regularization scheme, so let me briefly explain the following computation. So here we have again quark one loop contribution, including a full expression of the propagator. And now we expand that full expression of propagator, so trace log S in powers of effective mass. The leading order is just the condensate independent term, which just determines the overall normalization. And the mass effective condensate dependent term start with the quadratic order. Okay. And so this diagram is of course UV divergent, but we have also counter term. And so it can cancel UV divergence. And as a total, this is UV finite. And this renormalization is nothing but the usual the renormalization of 2-point function. And similarly, for quartic order, we have some 4-point function. The quartic order of effective mass appear to be this graph. And this diagram can be divergence can be cancelled by the counter term from the vertex. And in this way, and this renormalization is nothing but the renormalization of 4-point function. So after performing the renormalization of 2-point and 4-point function, the quark contribution, one loop quark contribution in effective potential is totally UV finite. And higher order 6-point function, for example, is UV finite by itself. So we don't have to do anything. Okay, and similarly, we can directly proceed to the finite density. And what is important is, so we would get, we now get the contribution from pion condensate. So this is quadratic order of pion condensate, but we also get the quadratic order of counter term, which can make this combination UV finite. And 4-point function can be automatically cancelled by vacuum counter term. And this off diagonal, this cross term between delta and MQ also can be cancelled by the counter term fixed in vacuum. And in this way, at finite density, all UV divergence can automatically cancelled by counter term, which has been determined in vacuum calculation. So all expression is UV finite if we properly renormalize the vacuum expression for thermodynamic potential. And so our renormalized effective potential made of 3 components. The first is 3 contribution. The second is renormalized quark single quark contribution, and UV finite. The finite counter term, which is UV finite. And this, what is most important is this quark contribution, which scale like mu I2 force at the high density. So this is responsible for quark behavior. On the other hand, 3-level part and counter term part scale like mu I2 square times lambda QCD square at high density, and which is subdominant at high density. Okay, so this is a structure of the effective potential. And let me briefly mention the role of 3-level potential first. So 3-level potential, actually there is an important term, which is a delta square term, whose coefficient is given by proportional to m pi square minus u for mu I square. So this sign, the sign of delta square term becomes change from the positive to negative value at the high density. So the sign change at mu I equal to m pi over 2. And if this sign change, then pion condensate is generated. So this is determined from the 3-level potential. And quark contribution includes the Dirac contribution plus a UV counter term, which cancels the UV divergence. And this quark contribution has the quark energy whose form is usual BCS form, ED minus mu I square plus BCS cap delta square. So this is usual BCS expression for the quark energy. So this is the structure of the effective potential. So now let us look at how chiral and pion condensate behave as we increase density. So in order to finalize our definition of the model, so we tune the finite counter term to reproduce the vacuum phenomenology. And here is the choice of parameter we try to fix through the renormalization procedure. And after tuning our model parameter, then we finally find the optimized value for the mean field, or optimized value for condensate. And this is a result. Okay, so this is a function of isospin chemical potential. And in dilute regime, okay, so basically one loop potential and the 3-level potential just coincide. And we have just a chiral condensate at low density, small chemical potential. And when chemical potential reaches m pi over 2, then pion condensate start to emerge, and we first have a BEC regime. But what is important is, so we start to observe the deviation from a 3-level computation and 1-loop computation. Okay, and the difference is dramatic. And this dramatic difference is actually a reflection of a physical difference between tree level and one loop calculation. At the tree level potential contain only meson degrees of freedom, and there is no information about quark. And so in very dilute regime, then a meson can be, it is enough to just regard a meson as elementary particle. But as we increase the density, then quark substructure should be important. And in fact, at the one loop level, we start to give the status of the composite particle to the meson degrees of freedom. So meson can be regarded as a composite particle only after we include the one loop correction. So in this picture, we have quark anti-quark contribution, and we have phi, the meson degrees of freedom, as intermediate state. So from tree to one loop level, we have a drastic change in our viewpoint. And this is reflected in the significant difference between tree level behavior of condensate and one loop behavior of the condensate. In one loop level, the quark substructure effect introduced the quark Pauli blocking effect. And then the pion gap, the gap of BCS gap is saturated to some finite value of order 300 MeV. So including quark substructure is essential, and it begins at relatively low density. Okay, so now I want to discuss the relationship between microphysics and the equation of state. And I particularly emphasize the impact of quark substructure effect. Okay, so let me start with equation of state at low density. And first, we want to make a comparison between our model result and lattice result. So lattice results are available at the density less than 0.6 times nuclear saturation density. And in such a low density regime, the result of a quark meson model and lattice QCD result are just consistent. And so this consistency is good, but actually this is not surprising because so QM model is basically can reproduce the chiral the result of chiral EFT because quark meson model respects chiral symmetry. Therefore, in dilute regime, it automatically reproduces the result of chiral perturbation theory. And since a chiral perturbation theory should be valid at low density, and therefore it coincides with lattice. So in summary, a QA model can reproduce a chiral result of lattice result in dilute regime. And this is not so surprising. So, but we are interested in the beyond the dilute regime. But unfortunately, lattice result with a good quality and with physical pions are not available at the higher density, and we have to wait for the new result. But okay, so any questions? May I proceed? Okay, so let me continue. So so what I'm really interested in is beyond this dilute regime or BC regime. But but I have to wait for the new result. But so therefore, the following result are basically the prediction from the model. Okay. So the first important point I want to emphasize is the tree level result begin to deviate from one loop result around in quantitatively around 0.5 times nuclear saturation density. Okay, here. And the quark substructure become important. So I already explained that there is a significant impact on the behavior of condensate. But also in terms of equation of state, the tree level result and one loop result coincide around up to this dilute regime, but beyond that, so tree level result, tree level equation of state and one loop equation of state change shows a significant difference. So this indicates the quark importance of quark substructure. Okay, so now I want to address the behavior of sound velocity beyond a dilute regime. So as I already mentioned, so in dilute regime, the lattice result and QM Koch meson model result are consistent. And if you look at the sound velocity square, so there is a rapid growth of the sound velocity as a function of density. So from BC to BCS regime, sound velocity grow very rapidly. And then it will make a peak around 0.9 times nuclear saturation density in Koch meson model. On the other hand, lattice result shows a peak around 0.4 times saturation density. And this model further can be extrapolated to high density, and sound velocity gradually relax to the so-called conformal limit. And it approaches the conformal limit from above. And this is a bit different from perturbative QCD, and I will explain the reason later. And so I have to briefly mention, so our result start to deviate around from the lattice result around 0.5 times nuclear saturation density, and we don't quite understand the reason for the deviation. And in fact, the behavior of lattice result is very difficult to explain from any parametric estimate. So therefore, I would like to rather wait for a new result. Okay, and now let me briefly get some insights by doing some quick parametric analysis. So we would like to understand the behavior of sound velocity in simple terms. So for that purpose, so we consider the pressure as a function of isospin chemical potential. So first I consider the ideal gas contribution, μI2 force, with a dimensionless constant. And I also consider the so-called power correction, which is μI square times the some dimensionful parameter like lambda QCD square. Okay, so let us just consider this sort of simple parameterization. And here I assume this coefficient A2 to be positive, referring to the BCS discussion. For BCS case, A2 is positive. Okay, so with given, if you give a pressure as a function of chemical potential, you can derive all other thermodynamic quantity like energy density, sound velocity, or susceptibility, etc. And sound velocity square can be computed if you calculate Ni, the isospin density, and isospin susceptibility. And the expression for this expression, we get a simple expression like this. Okay, and so now let us consider two different regimes. So if A0 term, the first term, μI2 force term, dominate, which should be varied at high density. In that case, this first term make just sound velocity square to be 1/3. Okay. And on the other hand, if the second term, A2, becomes dominant, so in that case, we forget about this first term in the numerator and the denominator, then our sound velocity square is just 1. Okay, so this behavior from here at relatively low density to relatively high density can be basically understood by considering this sort of power correction. So this is a simple parametric consideration. So now let me discuss more detail about the growth of sound velocity, okay, in this domain, okay, in the context of Koch substructure. So the useful quantity to look at is occupation probability of Koch states. So this occupation probability can be computed if we have information about Koch propagator. And this is a typical quantity to be computed in BCS theory. So basically, in dilute regime, the Koch occupation probability simply grow into the vertical direction. And as we increase density, the direction change into a horizontal direction. And then we start to observe usual Koch Fermi sea. So this sort of evolution can be understood, convenient way to express this evolution is to divide the evolution into two distinct regimes. The first distinct regime is the evolution into the vertical direction. And the other regime is evolution into the horizontal direction. So this full evolution can be understood by the combination of this vertical and horizontal evolution. So let us look at the impact of each regime. So in vertical evolution, so occupation probability of quark state is simply scaled up by the density. So vacuum momentum distribution. And as we increase density, its height is just scaled up as we increase the density. It is proportional to Ni. And in this regime, so we want to look at the pressure. And the useful way to look at pressure is to focus on the pressure is given by energy per particle, which is differentiated with respect to the number density. Okay, so the average energy of a particle. So how average energy of particle change with density is actually reflect the size of pressure. So if energy per particle doesn't change, okay, so this happens, for example, in non-relativistic limit. In that case, pressure is small. Okay, so and this discussion can be expressed in general way. So this vertical evolution, during this vertical evolution, energy per particle doesn't change much. Therefore, pressure is small. Okay, and that leads to soft equilibrium state. On the other hand, when the evolution becomes evolution happen in the horizontal direction, and in this case, we can easily see energy per particle grow up. Okay, energy particle naturally grow up as we increase the density in this way, and in that case, pressure is naturally large. And this large pressure is happen naturally in quark matter regime. So it leads to the stiff equilibrium state. So then the weather equilibrium state, stiff or soft, can be well characterized by looking at whether evolution is happen in the vertical direction or horizontal direction. And in fact, if you look at the dilute regime, then vertical evolution is basically dominant. So this is the occupation probability divided by the occupation probability in the vertical evolution regime. So if this one is if Fp over Ni times F vacuum, phi vacuum is just a constant. So this is just just a scale up in the proportion with proportionality with number density. Then in that case, equation of state is soft. But as you can see, the vertical evolution is the regime switch from vertical evolution to horizontal evolution around at density around 0.3 times nuclear saturation density. And this change in trend is well reflected in the behavior of sound velocity. So during this vertical evolution, sound velocity square is less than 1/3. And after switching of the regime from BC to BCS, quark substructure become important, and sound velocity grow beyond 1/3. Okay, so this regime is what I discussed in the BEC regime. Here, sound velocity is small, and from the change of the regime from BEC to BCS regime, sound velocity grow up rapidly and relax to the usual conformal limit value 1/3. So this is the understanding. Okay, so now. So in the last 15 minutes, I will mention the high density regime for the strongly correlated quark matter. So what I want to discuss is this domain. So how the sound velocity relax to the conformal limit, conformal value. So at high density, we naturally expect the validity of perturbative QCD calculation because of the asymmetric freedom. And nowadays, there have been growing interest in perturbative QCD as a boundary condition. Because as I emphasized at the beginning, the causality and thermodynamic stability correlate different density domain. So therefore, pQCD result can be used as a useful boundary condition to neutron star physics. So, and so another important question is recently people are interested in the behavior of sound velocity and also the trace anomaly. And where it is known that learning of the alpha S is very important. So EOS is conformal if coupling doesn't run. But for this, in this context, so there are several natural questions come into our mind. The first question, so if learning is so important, so how important is the lambda pole at the low energy regime? So that's first question. And the second important question is how large the impact of the non-perturbative power correction. So as we know from the hadron spectroscopy, so the pQCD computations are not enough when we compute hadronic correlation function, but we have to do the operator product expansion, for example, that introduce the power correction, so lambda QCD square over Q square something. And this, the power correction proportional to lambda QCD is non-analytic in the coupling. Therefore, it cannot be calculated from perturbative calculation. So it is intrinsically non-perturbative. And we are interested in how large the impact of these corrections. And also, we are also interested in the normalization of equation of state, which is sometimes called Bug constant. Because the perturbative QCD is done for around some trivial vacuum without a condensate or non-perturbative correction. But our true QCD vacuum is non-perturbative. And if we do the perturbative calculation, there is a difference in the normalization of the equation of state. And we are interested in the impact of such constant. Okay, and the first question. So let us consider the learning of alpha S. So alpha S computed purely by perturbative calculation, and or the learning of alpha S which freeze in the infrared limit. So this has been discussed in, for example, Schwinger-Dyson equation in Landau gauge or some holographic calculation. And this is some example of calculation alpha S. With some renormalization scale parameter, which is related to the chemical potential by some coefficient x. Okay, so we vary x from 0.5 to 2. Okay, so this dotted line is a pure perturbative result for learning, and this solid line is some interpolation between some model, the model with IR freezing coupling and the pure perturbative calculation. Okay, so we consider the two different type of coupling with different x, and then look at their impact on the perturbative pressure. And what we found is rather bit boring. So this shaded region corresponds to the upcore chemical potential of 1 GeV, where perturbative QCD has been used. And below that, only at the density lower than this regime, we start to see the impact of the difference between perturbative running and IR freezing running. Okay, so therefore, so no substantial impact for low density regime in the context of perturbative QCD. So pQCD is just used for this regime. Okay. Okay, so next question is the impact of power correction, which is non-perturbative. And so the order of magnitude can be understood from the size of gap and the phase space. So the size of gap is delta, and the phase space available for the condensation is 4 pi pf squared times delta. And we have 1 over 2 pi cubic for overall normalization, which comes from the integration of momentum. Then a naive estimate for the non-perturbative correction from condensate is order mu I square delta square over pi square, where this overall coefficient is order 1. Okay, so now let us add this contribution to pQCD contribution, and then examine its impact. So the first question for such exercise is the size of delta. And from lattice QCD, the critical temperature for pion condensate is order 160 MeV. And if we use a naive BCS formula, then the size of gap is estimated to be the order of 300 MeV, which is the order of lambda QCD. And in case of a Koch meson model, we obtained the order 300 MeV. And next question is, what is the delta at higher density? So this estimate is based on the lattice result around saturation density. And the question is how large the delta at the even higher density. And so for isospin QCD, we don't have direct information, but there is some similar exercise for two-color QCD. And so such calculation examine the delta at the higher density. In two-color QCD, we have a dipole condensate instead of pion condensate. And the system is very similar. And from those calculations, the hint we obtained is so lattice critical temperature is not very sensitive to the core chemical potential for the relatively wide domain from 300 to 800 MeV. So therefore, because system of two-color QCD and isospin QCD is similar, we expect a similar insensitivity of the gap. So the reason why this critical temperature or gap, size of gap is relatively insensitive to mu q is so delta may be created by semi-short range correlation rather than a super long range correlation. Long range correlation should be screened off, screened by screening, etc., etc. But if delta is created by semi-short range correlation, it is not super sensitive to the screening. So this might be the possible explanation. But anyway, I just assume delta is just insensitive to the value of chemical potential. So within that assumption, so let us look at some the impact of power correction. So here, so this is the perturbative pressure plus power correction divided by normalized by Stefan-Boltzmann limit. Okay. So here I choose renormalization parameter, renormalization scale. So X for renormalization scale to be 1. So this is just a standard choice. And then for this renormalization parameter, I change the size of gap from 0 to 400 MeV. So relatively wide range. So as we increase the size of delta, then initially without the gap, it is just from high density to low density, the pressure simply decrease monotonically. But if there is the delta of order 200 MeV, the trend change toward lower density region. Okay, what the important message is the power correction itself is not large in magnitude. So around here, it is at most a 10% effect. Okay, but it can change some qualitative trend. For example, in the sound velocity, okay, so there is, so we again look at the impact of the power correction delta. And this band is given for the X from 0.5 to 2, okay? So this upper bound is given by X equal 2, and this solid line is given by X equal 1, and the lower bound is given by X equal 0.5. Okay, and so if we just omit the power correction, then we just simply reproduce the standard perturbative behavior. That is the sound velocity approach to conformal limit from below, like this. But if delta is order 200 MeV, Then for x equal 1, the sound velocity approach to conformal limit from above, like this. And if the delta is even bigger, then the sound velocity approach from approach to the conformal limit from above with substantial strength of the number. So this sort of power correction is important, even when its magnitude power correction is just 10% or 5% effect. It still has a power to change the trend of the sound velocity. Okay, the final topic I would like to discuss is the trace anomaly. So recently there have been growing interest in trace anomaly, driven by Fujimoto et al. So trace anomaly is just a signal of the violation of scale invariance. So non-zero expectation value of trace anomaly just indicates the violation of scale invariance. So let us compare 3 different kinds of states. So if we just look at a single hadron state, okay, then the expectation value of energy momentum tensor with respect to single hadron state with momentum k is just is given by k mu ku divided by mh, okay, hadron mass. So this is general parameterization. And we don't have a G mu nu contribution because it does not satisfy the conservation of energy momentum. Okay, and now, so for this, because we are talking about single hadron states, we can always take rest frame for each for that hadron. So let us take a rest frame. Then the TII contribution is just vanishing because Ki is 0. Okay. So therefore, the trace anomaly is simply given by the zeroth component of the energy momentum tensor, which is nothing but the just mass of the hadron, which is positive. So if you consider the many-body system, but still ideal hadron gas, then in that case, we observe the impact of Pauli principle. So some hadrons must have a finite momentum. So not all hadron can be at rest in many-body system. So for ideal hadron gas, so the TII component, the special component is now is finite, so proportional to k square. And by lowering the index I, then now we have the TII component, which is negative. Okay, so trace anomaly in that sense, in many-body system can be negative in principle because of the this special component. And finally, in matter, T mu mu is just, it is well known that T mu mu is related to E minus 3 times pressure. And according to this argument, so we can, or from this expression, we can see the trace anomaly can be either positive or negative, and approaching 0 in the relativistic limit or conformal limit. So this is how the sign of trace anomaly would change from single hadron states to the states with many-body system. And so Fujimoto et al. Made some conjecture. So perturbative QCD constraint for the trace anomaly is just gives a positive trace anomaly. And then they made some interpolation between chiral AFT and pQCD for different type of interpolation. And then they conjecture the positive trace anomaly for the reason I don't fully understand. But anyway, so many people nowadays try to check this conjecture. And here I want to make some little contribution to this argument. So again, let us consider some schematic expression for pressure for the equation of state. So so this is for perturbative QCD expression with A0, including the running alpha S. And now I add a new contribution, the power correction A2 mu I square. And also I further consider the at the constant which comes from the normalization or a bug constant. Okay, and starting with this expression, again, we can compute the pressure, energy density, etc. And now trace anomaly can be parameterized in the following way. The first term comes from dominated by a learning of alpha s coupled to mu I2 fourth term. And power connection generate the negative contribution if A2 is positive. And overall normalization of bug constant at the positive contribution to the trace anomaly. Okay. So the learning of alpha s has been studied, of course, and which gives a positive contribution. And also the overall normalization gives a positive contribution. On the other hand, if we consider the power correction or non-perturbative correction, which have not been considered, then we would get a negative contribution to the trace anomaly. And if these power corrections are large enough, then it can change the overall sign of trace anomaly, and which violates the positivity conjecture. But what I would like to stress is, so I'm not so interested in whether trace anomaly is really positive or negative. The conjecture itself is not not of my main concern. But if trace anomaly turn out to be negative, then it is very likely to be the indicator of a non-perturbative correction or non-perturbative physics, like color superconductivity or Hawking matter. The negative trace anomaly can be the indicator of such non-perturbative physics. So here, now I come to the conclusion. So let me summarize. So the first, the soft stiff type equation of state has been indicated from nuclear physics and neutron star observation. And so it's to explain those qualitative behavior, Quark degrees of freedom seem to be essential. Especially, so extrapolating a purely hadronic model toward very high density encounter several problems, such as convergence of many body forces, even before hadrons overlap. And the second part, okay, and the and secondary, so okay, so we studied the Quark measure model, and the Quark measure model may capture the physics from low to high density because it includes the Masonic degrees of freedom and also Quark degrees of freedom. And at low density, the model respects the symmetry of QCD, therefore it naturally reproduces lattice results. And at high density, DOS is dominated by Quark degrees of freedom, as it should. And the third point I would like to stress is non-perturbative correction introduce a number of new qualitative features which have not been fully appreciated. So at low density, the power correction, which are attractive, can stiffen equation of state, and sound velocity is substantially can be substantially larger than the conformal value. And at high density, power correction would affect the perturbative QCD boundary condition, which have been used to constrain the low density region. So I don't know fully. So how actually whether how important power correction is of course due to just a quantitative issue, which should be studied in more detail. And to check the physics beyond the BEC regime in isospin QCD, we would like to see lattice data at the higher density, especially up to 5 times nuclear saturation density, because interesting physics occur somewhere from BEC regime to the BCS regime. Okay, and with this, I stop my presentation, and thank you very much for your attention.
Thank you, Toru, for this very clear and entertaining talk. I liked it very much. I have lots of questions, but
okay,
I'm happy to have other people ask their questions first.
Yeah.
So please, if you have a question, unmute yourself and ask the question. seems like people are shy, so I'll go ahead and ask my first question. So basically, one of the first questions I have is, so these lattice simulations, this is, we're talking about QCD at finite isospin chemical potential, right? And so the results you've presented, you said, I think, that you can go up to about 0.5 times the your N naught, your nuclear metal acceleration density. What's the reason for having to stop there? Is it numerics? Is it just the size of your computer? What's creating this limit?
I think, yeah, I think computing time. So previously, people study actually, yeah, perform simulation at higher density. Yeah, before, yeah, actually, we refer to the result by Brandt, Endroghi, etc., and their studies are much more careful compared to the previous study. And so, yeah, and yeah, I think it takes time to go to higher density if they demand the quality. Yeah, but the more rough calculation were available before. Yeah.
So okay, fine. So basically, if you get a bigger computer or more running time, you can extend it. But so what's the? Do you have any estimate of the cost? Like, if I wanted to go to 1 times double the amount in density, 1 times nuclear metal saturation density, how much bigger does the computer need to be in order to sort of do that?
Yeah, I don't have feeling, but I have to ask. Yeah, Georg.
Shouldn't the constraint here be that the density has to be, you know, some amount below the lattice cutoff? Isn't that what?
Sure. Yeah. Yes. So yes. Yeah, to avoid lattice saturation effect. Yeah, we need a bigger lattice and also finer spacing.
So the constraint is A cubed because it's a volume?
Volume as well as the lattice spacing. Yeah, lattice spacing is related to UV cutoff, and on the other hand, the volume also related to the low momentum.
So naively, if I am able to run a simulation where the lattice spacing is half of what I used to have, that gives me a factor of 8 in the density. Oh, I see.
I think that's right.
Great. Okay, I'll pause here with my questions. See somebody else wants to ask a question. Now is your chance.
I maybe ask one quick question because I have to leave quite soon. So first of all, Toru, thanks a lot for this very, very interesting presentation. This was really a pleasure to watch. So my question may be very naive. I don't know so much about all of the conductivity. So one thing that struck me as surprising were the very large values that you were using for this delta parameter, the superconducting gap. And I understand that this comes from your calculation, but my question is that because I'm used to thinking of the relevant gap for calculations in terms of baryon chemical potential being of the order of 100 MeV or less. So my first question is this delta that you are considering exactly the same delta that we should also be considering when we are not thinking about the isospin chemical potential, but the baryon chemical potential? And second, how do these values of your several hundred MeV, how do they compare to other calculations in the literature?
Yeah, you're asking about for QCD, right? Not isospin QCD.
Yes.
Yes, I understand. Yeah. So people mostly use the Son's estimate. Yeah, and if we naively use that formula, it can be about 100 maybe. But of course there is a large uncertainty of several factors. So honestly I don't know. Okay. Yeah, but potentially it can be as large as 200 maybe in principle. But the point I want to make is we should prepare for such kind of possibility. Yeah. So 200 maybe is not so unnatural, I would say.
Sure.
Yeah, it is possible. Yeah.
Thanks a lot.
Yeah.
Okay, since I have a follow-up question to that, I'll ask my follow-up question, and then somebody else can chime in. So my follow-up question is, I think you mentioned that you cannot measure delta from your lattice calculation.
Actually, I didn't say that.
Yeah, that sounds
yeah, in principle, they can do.
Okay, so why don't you just go ahead and do that? And we know.
Yeah, of course, if they give us such data.
Okay, so it's basically just
so in principle,
to...
it is doable. In principle, doable. Yes.
But that, if I understand correctly, that would, in broad brush strokes, settle the debate, because if delta comes out to be 10 MeV, then most likely that is not responsible for your peak in the sound curve, right? Because it's too small. But if it comes out to be 200 MeV, then oh yeah, sure. Then there's all sorts of other reasons why we sort of, well, have not thought such a large value to be sort of likely. Let's put it this way.
But even before directly computing delta, so we can somehow get some insight, order estimate from the critical temperature. So if delta is order 10 MeV, we cannot get the critical temperature of 160 MeV. I think it's very difficult. So so usual common sense is critical temperature and the size of gap is the same magnitude. And if we just naively use BCS expression, then usually delta is about twice bigger than critical temperature. Of course, this is rather naive, and it's much better to directly compute delta. Yeah, I agree.
Yes, I agree too.
But delta should not be so small.
I see.
Yeah.
Okay, yeah. Any other questions before I go on?
I have a question.
Please.
So you said that you were taking the gap to be constant, but don't we expect from like Son's estimate that this should go to 0 at higher densities?
So of course we can use also Son's expression. But actually, the reason why I took rather a constant value for gap is from the study of two-color QCD. Then critical temperature is relatively insensitive to the chemical potential. And of course,
remind me. Sorry, you said that was up to some density, right? That's been
from 300 MeV to 800 MeV, the critical temperature is almost constant. So that's the reasoning. But of course, in principle, delta can change, and in naive sense, delta should increase toward a lower density. That's the usual way of thinking, I think, because coupling is simply bigger.
But just to interject here, for QCD at finite baryon density, we expect TC to actually be quite dependent on it, right? We expect it to go down. So if you sort of make this same estimate by sort of equating delta with TC, then we do expect it sort of go down at higher density, or did I sort of misunderstand something?
There are two effects. So as we increase higher density, then we have more phase space available for the pairing. On the other hand, the coupling constant becomes weaker at higher density. So there are competition, right?
Yes, I guess so, but I just had the phase diagram shape in my mind for finite baryon density, where we usually sort of have this sort of quite steep drop of TC as we go to baryon densities on the order of unity or larger.
Sorry, the critical temperature decrease at the higher density.
Yes.
So that's basically due to the running of coupling, right?
Well, okay.
Reaction.
Well, I don't know. I mean, those scales, I think it's all non-perturbative. So I wouldn't be able to sort of say why it is that it does that. But Sorry, Tyler, I didn't mean to stop you. If you have a follow-up to yours, please go ahead.
No, I think that's fine. But also, you can't just use TC everywhere, right? Because, for instance, there isn't pairing at low densities, but TC still is there. So I guess this estimate should only work as the density is sufficiently high where you do expect pairing.
Your estimate for, sorry, what?
So what I was saying,
yeah,
in the phase diagram, there is a value of TC as you go to lower densities as well. But I guess, are you saying because it's a crossover, you can't use the same argument?
From here to? But I didn't fully digest your question, sorry.
I was just thinking back at like Paul was saying in terms of the phase diagram, where you do still have a value of TC as you make the chemical potential smaller and smaller, but you don't expect there to be pairing as the temperature is very small, right? Or do you expect there to be pairing all the way down to very low temperatures, very low densities?
So very low.
In full QCD, not isospin QCD.
For full QCD, for usual QCD. Yeah, so pairing itself, so okay, so that pairing, usual dicoc pairing or correlation can always exist inside of hadron. Like which can be observed from the nucleon delta mass splitting, for example. So so in that sense, such kind of dipole correlation exists, but that occur inside of hadron. And in some sense, the strength of pairing itself, I think it keep growing toward a lower density. Okay. Toward lower density, but it is eventually such pair will be eventually confined into hadron. So it's not like usual BCS Cooper pairing. What should I say?
I think that already clarifies some things for me. So thank you.
More questions? Okay, I have one more question, and then
Sure.
we are running over time, so we should move along. But so you are presenting results for QCD at finite isospin chemical potential. How much of the results that you presented do you think just carry over to QCD at finite baryon density, and which one you think will not?
So first one of the motivations to study isospin QCD is to confirm the mechanism for this peak for the sound velocity peak, and it is seems to be related to the quark substructure effect, but actually how to say compared to the usual baryonic matter, the mechanism is not so clear cut. So what I want to say is, before studying the isospin QCD, we did some schematic study for usual baryonic system. And the logic we found is the following. So in dilute regime, so baryons are just non-relativistic. And if we go to high density, of course, we have a quark matter regime. And because of the quark substructure effect, baryonic behavior must are forced to change into the quark matter regime. And this rapid growth of the pressure is forced by the quark substructure effect. Okay, so initially we have a small surround velocity because we have just non-relativistic regime, but it is forced to change into quark matter regime, and there we have a peak, and then in quark matter regime we just have the conformal behavior. And this picture is rather simple, but in isospin QCD, actually, so we from very early stage we already have the rapid growth of the sound velocity before fully having the this saturation effect. So the results are a bit not as clear cut as I expected. Yeah, that's one thing. And the other thing is, on the other hand, the high density behavior of the equation of state. Okay, so yeah, many people say, okay, isospin QCD or two-color QCD, we have just bosonic degrees of freedom, therefore it should be very different from a QCD. But if we go to sufficiently high density, we inevitably have the quark Fermi, and the pairing is just like the BCS type pairing. And that physics should be common to the three-color QCD. And the difference is the condensate is not gauge invariant. Therefore, we need some additional discussion. Yeah, but the bulk property should be the same. And we can get some insights from isospin QCD or two-color QCD.